So, title of the talk is Lattice, Path, and Heaps. So, I have to adjust with the 3 screens. So this is a lattice. This is a path, a dick path. And this is a heap. Maybe you don't know at all what is a heap. There is different formal definition. So I will just give an intuitive definition of what is a heap. So some diamonds fall down on the ground, and some diamonds fall on the ground. Some diamonds are touching other diamonds. And what you see at the end is a heap of diamonds. Maybe it can fall down with different way, but this is a picture, the idea of a heap of diamonds. So you see a diamonds, the video is slower than. So diamonds is just a pair I plus 1 of 2 consecutive integers. And if these 2 diamonds intersect I plus 1, then they are going to touch. If they don't intersect, they will not touch. This is another example of a heap with the lattice is a hexagonal lattice. And the pieces, you see, is hexagons. And they fall one over another. So maybe they are disjoint. Maybe they are touching another diamonds. And what you see at the end is a heap of diamonds. Maybe you don't see because it's everything is, but maybe you see this in a better way. And you see this is a pyramid. There is only one hexagon on the top that you can see in full size. So recently in Archive, in the last few months, there was many papers in totally, completely different subject on loop erasing random walk at spin system observable, Fibonacci polynomial, growth rate and 3D heaps of pieces, or counting words, the last array self-avoiding polygon since August, September, October, November, and in December, about fully commutative elements in Coxeter group. And a very nice paper by John Ziegler and our friend Christian about bounded dick path, bounded alternating sequence, orthogonal polynomial, and reciprocity. So all this paper, they use in more fundamental ways the notion of heaps of diamonds. So I'm not going to explain all this paper. I'm going to extract something which is common to these papers. And I will start with, also there is a paper in February about Aldo's broader theorem, about the random spanning tree in a graph. And so I will start with this very beautiful paper, 70 pages. So maybe another title of the talk would be an introduction, some comments on the paper of Christian and John Ziegler. Another title would be an introduction to the theory of heaps of pieces. And maybe another title would be from a work about many different topics, Reciprocity Theorem, commutative element in Coxeter groups, Ising model, hard hexagon model, zeta function on graph, and many cube SL function, orthogonal polynomial, and Lorentzian quantum gravity. But I need a whole day to do this topic. So let's go to more simple things. The notion of reciprocity. I start with elementary, the paper of Christian and Ziegler. So you have a dick path, and I did not see 2nk, the number of dick paths of length 2n, which are bounded by height k. Here, I should point with this one. here is a bond, and the generating function for this bounded disk path is well known to be a rational fraction. So I have to adjust because when I click, it takes time that the slides come, and then I click to the next one. So I have to adjust. Sorry if there is some few. And it's well-known subject that if a generating function is rational, so you have a linear recurrence relation, and you can extend this linear recurrence relation to negative integer. And so you can define A index minus n for n negative. And sometimes there is a combinatorial meaning. This is called combinatorial reciprocity law. So it started in the first non-trivial example was given by Erhardt. He was counting in a polyhedron point with integer coordinate. And there is a very beautiful reciprocity theorem on this, which was emphasized by Richard Stanley. This is a seminal paper by Richard Stanley in 1974. He has many reciprocity theorems with beautiful combinatorial interpretation. And if you have the generating function, the rational generating function for the object an, then the rational generating function for the negative integer, you have to change t in 1 over t. And so you have to, in possibility, if you know a combinatorial interpretation of an, can you give a combinatorial interpretation of A index minus n? Even there is a book now on all this reciprocity theorem. And in their paper, John Ziegler put in a message in Math Overflow in September 2020, and he says that this negative Catalan minus 2n is equal to this determinant. A beautiful Hankel determinant. And then immediately Richard Stanley say that this Cn, this number is interpreted by alternating sequence. See, the sequence of number between 1 and k, and they go up, down, up, down, up, down, up, down. So this is a combinatorial interpretation of the Catalan, bounded Catalan index minus n. And then Hopkins show immediately also on overflow that these alternating sequences are in bijection. They are given by this determinant. So this determinant is the Hankel determinant. There is a well-known theorem which tells you that the determinant is interpreted by non-crossing paths. And you see it is bounded by a certain height, 2k plus 1, and these non-crossing paths are in bijection with this blue sequence of blue numbers. Each time you see your blue numbers, when you take a vertical line, then there is a free possibility, and you put the number here is 1 plus the number of paths which are below this red point. And so it's easy to show that you get an alternating sequence. And here is an alternating sequence in bijection with the Hankel determinant. So you have to show that these alternating sequences are the interpretation of the negative Catalan number bounded by height k. So we denote alternating sequence with odd length bounded by k. And in the paper, this is the introduction of the paper. In fact, the paper is much deeper. They call this, it's the tip of the iceberg. And they are going to take the iceberg and show all what is below. But what is interpretation if you take an even sequence, alternating sequence? The Hankel determinant gives you odd length alternating sequence. But what is this interpretation? It's no more dict pass. You have to distinguish odd and even. And the interpretation is with this pass. It's pass like a Catalan pass, but bounded by height 2k plus 1, and going from the point 0 to the level k. And they claim that the reciprocity theorem for even alternating sequence is exactly this number, d minus the negative index of this number d. It's an analog of Catalan, but the paths going from 0 to level k, they are bounded by k. So you have to find the generating function for such bounded paths, and then take the inverse t over 1 over t, and show that you can go from the two combinatorial interpretation. So first, I start with a very well-known loop erased random walk. So you have a graph, you have a set of vertices. I just remind you this elementary definition. You start from a point, and then you are doing, as soon as there is a cycle, then you delete the cycle. And what you get, you see, this is well known in probability, etc. If you have any path going from U to V, then you can associate a self-avoiding walk going from U to V. And there are many studies, but we are in an ecological time. It's a waste of cycle. Can you imagine all the cycle you are going to throw in the trash? So a good way to study this loop erasing random walk is to keep the cycle and to have a bijection between path and a pair. The pair is a loop erasing random walk, the blue path, plus what remains when you take off, you put on the trash all the cycle. So you know all these SLE, Schramm lower evolution, etc., etc. There are many things in probability. You know this much more than I know. And so first, in the Heaps theory, there is 3 fundamental lemmas. And with these 3 lemmas, you can do many things. You can rewrite all the classical linear algebra. You can do many things. And the first fundamental lemma, it's a bijection between paths and some heaps of pieces. So when I have done this process, you see, I have thrown away these 3 cycles. So if you keep each of these cycles, if you keep them, in each order they appear, and if you know which point of the cycle was fixed to the path, then, of course, you can completely reconstruct the path. So you associate to such path a self-ordered path, a sequence of pointed cycle. The point is where the cycle was detached from the path. So, of course, you can reconstruct the path. But this is not a bijection. There is some constraint of the sequence. So you can forget the red point, which the point where the cycle was fixed. You can forget completely the red point, and you can reconstruct it, so forget this. And so you just take the sequence of cycle. So cycle is up to a circular permutation, like the cycle of a permutation. But if you keep the sequence, this is too much information. So what you have to do is different sequence will give the same path omega. So what you have to do is to take a heap of cycles. And you see these 3 cycles here. This was the first cycle. The first cycle fall down here. The second cycle fall down here. The third one. So this was the first, second, third. But if we do first this one, then this one, then this one, then it will be the same path at the beginning. So making a heap This is a heap of cycle. So there is it's like the dimers falling down one over another. But you see here, the red cycle is going to be above this cycle because they share a common vertex. This vertex here of the graph, or this cycle also, is above this one. These two, if they fall down, they are disjoint, and you don't know which one fell down before. So the analog of the touching with dimers is cycles are touching if they have a common vertex. If they have no common vertex, then they will be completely disjoint, and we don't know which one was fall down first. So I just keep the idea, intuitive idea of Heaps. And the blue path, the self-avoiding walk coming from the loop erasing random walk, there is a condition on the blue path and the Heaps of cycle. So we have the Heaps of cycle here, and you have the blue path. So see, I call this a dependency relation. If you have a cycle, the set of vertices is the support of the cycle, and the dependency relation is if the two supports intersect. So one cycle will be above another one. And there is a second condition. About the blue path, we are going to say it's a maximal piece of the heap. So what means a maximal piece? You have a heaps of cycle, a maximal piece, with some condition between the heaps and the maximal piece. So what is a maximal piece in the heaps? I go back to the intuitive definition of a heaps of dimers. So you see, maximal piece means that you can take off the piece without touching any other cycle. You remember the heaps of a pyramid of hexagon? Maximal piece was the piece you can see in full size. And so there is a bijection between a pair, a path on any set X, and a pair eta E, where the eta is a self-avoiding path going from U to V, and E is a heaps of cycle such that the maximal piece of the heaps of cycle, the projection of this maximal piece, intersect eta. So the cycle and the path in blue path have a common vertex. So this is a picture you see on the top. So any path, this is a fundamental, one of the fundamental lemma in a heap theory. Any path going from U to V is in bijection with the pair, the blue path, a self-avoiding walk coming from the loop erase random process, and a heaps of cycle. I recall you, cycle is up to circular permutation. And there is a maximal piece in the heaps of cycle. This is the red part. If you take only the heaps, you can take off the red part. And then the condition is that this blue path intersects this maximal piece. They have a common vertex when you project everything, the picture, on the ground floor where the paths are working on the ground floor. Even you can put some weight on the edges. The weight is just a formal variable for the edges. And the weight of a cycle or a path is a product of the weight of the edges. And then so the weight is preserved. And because in this bijection, the number of times a certain edges appear in the path omega will be the same as the number of times it appears in the heaps. And so the weight is preserved. And also this inversion theorem, you can work with all kinds of weight of paths, so you have a wide variety of possibility of proposition. So you see this paper, I will maybe, if I have time, give a few words on this paper. You know, this random, all this random, there is a Wilson algorithm. There is this, in this last paper, there is the Aldous Broder theorem with Fredes and Marquette. So they use the heap theory to improve, to study, to have better result about this process of taking a random spanning tree And random spanning tree is using loop arrays random walk. And if you work with Heaps, then it simplifies, it's enriched, and you get better proof for all these domains. So I will give an example, simple example with dig pass. So I will take my dig pass, not really a dig pass, going from level 0 to level k, and bounded by level k. It's more simple than the dig pass. It's going to give me even alternating sequence. Dig pass give me odd alternating sequence, but this case is more simple. So here you have a this kind of path, and then I'm going to, with my mouse, to follow the. So see, you follow the path. A cycle fall down. Then the cycle, then you go here, here, and then you make a cycle. Fall down. Then you go here. Cycle, fall down, and then you continue until here, and then you go back here, cycle, fall down, then you go here, cycle, fall down. So I need to lift to see better what is happening. You follow. See, and at the end, you have in blue, you have the path eta, the self-avoiding walk going from U to V. U is 0, V is the rightmost point. And then you get a heaps of cycle, which became, in fact, inversion with a heaps of dimers. So, in fact, in that case, this path on the right is in bijection with any heaps of dimers. You can take off the blue path, the maximal piece, you don't care about that. So this is why the even case for alternating sequence for the Christian and Ziegler paper is more simple, because I have all kinds of heaps, general heaps of dimers on a finite segment. So with dig pass, now I have a dig pass. And then I am going to have the same, show you the bijection. So I will start from 0. And then I go here, then it's fall down. I go here, so I go faster, and then I finish at the end. And so you get a heaps of cycle, which is in bijection with a heaps of dimers. And now the self-avoiding walk in blue going from U to V. U equals 0, V equals 0, so it reduces to a point. So it's a pyramid. There is only one maximal pieces, pyramid of cycle plus a point. And in fact, I delete the point, and I say it's a pyramid of cycle, of dimers, with only one maximal piece. You see, this is a pyramid of dimers with only one maximal piece in blue, and the dig pass is in bijection with what usually it's called a semi-pyramid of dimers. Semi-pyramid of dimers on the segment is a pyramid of dimers such that the maximal piece is, the projection is a dimer 0, 1. So you have this bijection. Dig pass, semi-pyramid of dimers on the segment 0k if you are bounded by k. So there is a bijection now between alternating sequence from the paper of Christian and Ziegler and heaps of segments in the even case. So I'm going to take heaps of segments. Segment is all the points between A and B. Special case is dimers is II plus 1, but now I take a much bigger of segments. And they are going to be in dependency relation if the intersection is non-empty. So this is an example of a heaps of segments. And I claim that there is a bijection between heaps of segments on a segment, on a finite line 0k, and alternating sequence of Stanley of even cardinality. And the algorithm, you are going to take off the pieces one by one, and each time you take the rightmost maximal piece. So the rightmost maximal piece is this one. Right? There is two maximal pieces. The rightmost is this one, and you delete it. And this maximal piece is 4, 5. So this is the two first term of the alternating sequence. 4, you increase to 5. Then it's delete. Then you take the next rightmost maximal piece. It's 4. When you have a point, a segment is 4, 4. A segment has two extremities which are the same. So 4 is 4, 4. And you see, 4, it's increasing and now decreasing. Now it's weakly increasing. Then you delete it. Next one is 2, 3. So 2, 3, 4, 2 is decreasing, increasing. Rightmost maximal piece, etc. Rightmost maximal piece. And because of the fact that each time you take the rightmost maximal piece, it's going to give you an alternating sequence. Because if you take a segment like this, so you take left extremity and then increasing, and if you take the rightmost, the next one will be a little on the left, because if there was another one on the right, it would have not been the rightmost maximal piece. So you get really an alternating sequence. Like this. This is the bijection. So the reciprocity theorem, we were starting from this path, the dn, not the Catalan path, but the dn path going from 0 like this, in bijection with the heaps of dimers, and the alternating sequences are in bijection with the heaps of segments. So the reciprocity theorem, I have to prove that I have to take the generating function of this, take the inverse f of 1 over t, and show that this is a generating function of heaps of segments. So the reciprocity, taking the inverse of t in the generating function, is going from heaps of dimers to heaps of segments. So there's a kind of reciprocity. And at the beginning of the talk, I show all this paper. It's because this idea of reciprocity between dimers and segments appear in all these completely different papers. In the fully commutative element in the Coxeter group, it appears again, the reciprocity between dimers and segments, but in a totally different context. So in the odd case, of course, I will go faster. In the odd case, then it's a little more complicated to take the dict path, alternating sequence in the odd case, because then you have the bijection in the odd case is you have a certain point, unique point here. It's the point A1, and then there is no maximal piece on the left, which is equivalent to say that in fact you have a heaps of segment. You make an artificial segment here, and this will be the maximal piece of the heaps of segment and the unique maximal piece. There is nobody on the left, and then you take the same process, but now the process is a little different. You are going to take the leftmost maximal piece, and you do the same, and you will get again an alternating sequence, but with increasing, decreasing, increasing, decreasing. You see it's a slight variation for odd. I go faster. And then there is a reciprocity, so between the semi-pyramid of dimers and heaps of segments, such that this point is a maximal piece, and there is no maximal piece on the left. And this is going to be the reciprocity for Catalan numbers. So taking the leftmost or taking the rightmost piece in the heaps, I am going to use this in a totally different context. In the paper, for example, for the fully commutative element in Coxeter group, it's exactly the same process which will be up here. So the reciprocity theorem, you have to show that the generating function of this, I just take the even case, the more simple. I take any the even case. The generating function for a heaps of dimer is f of t, and taking the inverse gives you a generating function of heap of segment. So why is this reciprocity? I need a second basic lemma on heaps of pieces. There is 3 basic lemmas, so this is the second one. It's the inversion lemma. Inversion lemma tells you that if you put some weight on the pieces, the generating function of heaps is the inverse of the generating function for trivial heaps. So this is trivial heaps. All the pieces are at the ground level. If you have dimers or segments, they are all at level 0. If you have cycle, they are all 2 by 2 disjoint, so it's a kind of permutation if they cover the whole graph. And you put some weight, any weight, a variable, polynomial. Only condition is that the weight does not depend on the height of the pieces. It depends only on the projection of the ground of the pieces. So in the inversion lemma, tell you that generating function of heaps is the inverse of the alternating generating function for trivial heaps. You have to put a -1, the number of pieces in the... So this is the denominator. And you see, philosophically, taking the inverse may mean taking heaps. Heaps is taking the inverse of a weighted generating function. An example, heaps of dimers on a segment, this even case. So the heaps of dimers on a segment is just the inverse of trivial heaps. And trivial heaps of dimers is this is a trivial heaps of dimers. This is sometimes called the Fibonacci polynomial. It is the sum of all matching of this segment. Say you put an x. Each dimer is going to be weighted -x. And sorry. So I will use, in fact, each dimer in the path, in the bijection between paths and heaps, each dimer is weighted xx, because the dimers count for 2 paths, 2 elementary steps in the path. And so the reciprocity theorem, you have to take the inverse of generating function of heaps of dimers, and taking the inverse of t, means that this is generating function for this polynomial, trivial heaps of dimers, and taking the inverse is taking the reciprocal polynomial. So you have just to change the xx, you put them here on the fixed point. Taking the reciprocal, it's just passing from this to this. And why this is taking just this reciprocal? Why it's going from dimers to segment? How to prove that this corresponds? Here is a heaps of dimers with a weighted is xx for each dimers. And here is a reciprocal. You put an x now on each isolated point, and you delete xx for dimers. This is a heaps of segment, a trivial heaps of segment. So each segment is weighted xx, xx, xx. So how to go in bijection between this and this? The bijection is here. Which is the heaps of segment. They are on a segment of length k, and the trivial heaps of dimers, they are on a segment of length 2k. I have double the number of points, and this is the bijection between trivial heaps of segment, trivial heaps of dimers, which explain taking the reciprocal polynomial, which explain taking the inverse of t, which explains the correspondence between this reciprocity. So this gives you a proof, combining all this, that the number of alternating sequence in bijection with the heaps of dimers is given by is a negative of this big path. So behind this there is Fibonacci, Chebyshev, because this Chebyshev is very close. It's just to replace x by 2x, and then you get this, what I have defined before, this polynomial Sn, which is Fn of x2. So in the even case, this reciprocity. For the odd case, it's a little more complicated, because instead of really general heaps of dimers, I have semi-pyramid of dimers coming from dict paths, and in that case, I have an extension of the inversion lemma, which says that the generating function for heaps of pieces such that the projection of the maximal piece belong to a certain set M, capital M. You fixed M, and all maximal pieces must be a projection in M. It's going to be the same denominator, but there will be a numerator. And the denominator is the same, but the numerator is a sum of trivial heaps, alternating sum of trivial heaps, such that the pieces does not belong to M. You see, this is D, this is N, this is the maximal piece. And if I apply this to this dict path, we have seen dict path is in bijection with semi-pyramid of dimers, so the maximal piece must be this. And if I extend this inversion lemma, I get the generating function for semi-pyramid of dimers is exactly, the denominator is the same, but the numerator is trivial heaps of dimers which are not, which does not intersect, which does not belong to this. So it's exactly trivial heaps of dimers on this segment. It's very easy, you see, it's a numerator. If you apply the extension of the inversion lemma, you get this rational fraction, which is very well known. And in that case, the reciprocity odd case, you have to show this bijection for the odd case, and you have to take the 1 over t in this rational fraction and show that you get the segment with a special condition. And this is easy to do also. An extension, as you go fast, it's just a slight. So this is the tip of the iceberg. This is just the introduction of the paper of Christian. So just an introduction to this paper, and with Heaps and introduction to heaps of pipers. So the iceberg I have shown you this visible part, and below there is much deeper. Paper is 70 pages, and so you see you can move this bounded part, bounded Hankel determinant. You can move the bound. So if I decrease the bound by 1, then I have no freedom. If I increase the bound by 1, 2, etc., then if you increase, you have more freedom. Now there is more red point. This is not completely free because this is not allowed this. So the more you increase, the more there is red point, and then you get some analog of alternating. You get tableau, all this. So this is a very deep, very beautiful papers. And behind this, there is orthogonal polynomial. There is because if you put some weight, there was a Chebyshev polynomial. So if you put some weight on the dimers, it's well known that then you get general orthogonal polynomial. And the moment, instead of heaps of dimers or pyramid of dimers, they become weighted pyramid of dimers. So all this work with weight. In fact, for general orthogonal polynomial, you need dimers and monomers. You need Motzkin path where there is a level. So, but all this you go through the general orthogonal polynomial. And this meeting, there was a talk by Murad Ismail, and here there is a new book where there is a connection between orthogonal polynomial and Heaps theory. So this is the first part of the talk about this duality between heaps of dimers and heaps of segments. So the second part, this same duality appears in the context of fully commutative element in Cox-Setter group. But before that, just a detour. Taking the rightmost piece, this reminds me of Andrew's theorem about the reciprocal of Ramanujan identity. What Ramanujan has to do here? See, Andrew defined quasi-partition. Quasi-partition is an extension of partition. It's a sequence where you are allowing this between two consecutive parts It's not decreasing. It can maybe increase a little. So this is a quasi-partition, 4, 4, 3, 1. So you see it's 4, 4 is decreased. But then you are allowed to increase by 1, at most by 1. This is a geometric representation of quasi-partition. And on those shows that the inverse of the denominator in the Ramanujan continuum fraction is a sum up to the sign of quasi-partition. So this is the denominator of the Ramanujan continuum fraction. So it's a trivial ellipse of dimers. It's a generating function of trivial ellipse of dimers, where each dimer is weighted by minus k, minus q power k. And so I am going to apply this theorem of 1 over d. I am going to apply the inverse. So the inverse of the generating function for these heaps, weighted heaps with a q, is the sum of heaps of dimers. So here, say each dimer is weighted now q, q2, q3, q4. And then taking the rightmost maximal piece, just take the rightmost maximal piece. So this is the first one, the second one, the 3, 4, 5, 6, 7. If you take the rightmost maximal piece, and each time you look this is the dimer 3, 4, so 4, 4, 3, 1, 1, you get a quasi-partition. So see, when you have segment, you get the alternating sequence of the first part of the talk. If you have only dimers, you get exactly quasi-partition. And so this is a proof of the bijective proof of Andrew's paper. This was in the 80s, and this proof appeared in Journal Indian Society in 87. And so I'm going maybe in the pages given by Cyril about the history of Lattice path. There was Désiré André, there was many people about the Ballot Problem. The Ballot Problem, there is a beautiful page by Igor Pag. You have a nice Catalan page, and you know the Ballot Problem was given André by Bertrand. Désiré André solves the Ballot Problem. Sometimes it's called the reflection principle, but it's not exactly the reflection principle. It's something given. And in fact, it was, everybody knows that it was first discovered by Whitworth in 1879. In fact, Delannoy also gave a proof of the formula for the Ballot Problem. And Delannoy is working in bounded Dicke paths in a certain way. This is rational. This is in 1888. Everybody believes that the generating function for bounded Dicke paths is given the same as in binary tree, bounded left with the left height on binary tree, and it was given in the paper by De Bruyn, Knut, Rice in 72. But Delannoy, he has given an analogous formula for bounded Dicke path. Not exactly the same. He was taking with the length of, there is a game between two players, and each time you have each player have n francs in their pocket. If you lose, you give 1 franc to the other player. If you gain, you get 1 franc. And so what is the probability that the game is going to stop when one of the gamers have no more money? And so this problem is to count such paths which are bounded between minus and n. So it's Dicke path with some bounds, and you have to touching one of this. And so they give formula. Delannoy, this beautiful formula, a combinatorial formula, and Rouchet also gave this formula. And this is explained in the 5th Lattice path conference, a paper by Cyril and Sylvian Schfer of this formula. But this is, maybe there is a philosophical implication in this, because this is two different philosophies of combinatorics. And I read there was a meeting in Guéret in 2015, because Guéret was the town where Delannoy was living. They organized a meeting, and they found some letters in the family of... and there was some letter of Catalan. And there was a fight between Rouchet, who used geometric function, determinant, everything. Delannoy used elementary method, what he called la méthode de l'échiquier, chessboard method. Means you are moving a tower on a chessboard, and here with the bound, it's a hexagonal chessboard. So he used this method in modern language. He used combinatorial, and then there was a fight because between these two methodologies, and this fight is described in the proceeding of this meeting in Guéret, because Catalan, he tried to defend Delannoy, and he submitted a paper to the, and paper was completely modified by Désiré André. Désiré André and Catalan was good friends for 30 years, so Catalan was not happy. He withdrew the paper, and he wrote to his friend Delannoy, and he said in his letter, Catalan et les effarouchés. So you have to, the joke is in French, cannot translate, Rouchet, the people with effarouchés. So you see it's typical of the 2 point of view, B calculus and combinatorial method. And this kind of duality appear until when I begin, when I was young, again, Bourbaki was against all this combinatorial method, everything. And so, in fact, if I translate this method, you see this is the path of Delannoy is this. So you have to take the genetic function of this and this. So it's analog. There is a Chebyshev, etc., etc. This is why there is this. This is the zero of the Chebyshev polynomial, etc. So you see much earlier. Bounded dict path was already in a different way. So I think Delannoy, if he was in this room, he would be happy to see a chessboard again with heaps of diamonds on the chessboard. It's not tower moving, but then it's, there is some progress in 140 years. Now I will make a detour through history. If you read this page here, there is a ballot numbers. There is a Catalan number. So look carefully. This number is the sum of this and this. So it's exactly the way to compute the ballot path. And in this book, you get a formula for this number. So who have written this? It was written in an 8, not at the Roman time, but at the French Revolution time.
What is the Sharaban number? From Mongolia?
No, this is not the Chinese Mongol. No, it's written in Arbogast, 1800, du calcul des dérivations. So it's much earlier. This is the first time the ballot problem is solved. 70 years before Wilsworth. I sent a mail to Igor Pak. He put this on his special webpage for Catalan number. So I say it's good to go back to the history. I discovered this in Metaglefler. My friend Alain Lascaux say all these students, they are always all day on the screen, and they don't know there is a fantastic library. They should go. And he told to me, go and see the book of Argobast. So I read all the book, and I found this. So it's good to go back to the source. Louis Lagrange was always saying, lisez Euler, read Euler. You have always to go back to the source. So let's go back to the duality between fully combinative elements in the Cox-Ether group. You have Heaps. So now I am with commutation. This is another way of defining Heaps. In fact, Dominique Fortin-Cartier introduced commutation monoid. And commutation monoid is, it starts with a thesis of Fortin about probability problem, and he translates it into combinatorial problem. Then with Cartier, they transform this into algebraic problem. And then the speaker transforms this into heaps of pieces. So there was a papers, and there is a video book where you can read all this, all what I have said. It's in this video book, and see if you click on it, it's. I made a mistake on the OK. So now instead of pieces in dependency, in concurrence, it's pieces in commutation. There is a commutation monoid. It's some letter with commute. There is a binary relation, and some letters commute. AB equal BA. It's a not reflexive relation. And for example, for heaps of dimers, now in dimers, so dimer sigma I plus 1, they are going to commute. This is the inverse relation. This is a complementary relation than to be one over another. They commute when they are disjoint. And they are one over another when they don't commute. So you see, it's a reverse way to see the heaps of pieces. So this is the two dimers which commute. And there is a commutation class. And this is two dimers which does not commute. And these two words are in the same commutation class. And the red word says they fall one by one in different order, corresponding to the word. And then I claim that if two words are in equivalence class, they give the same heaps. And conversely, if they give the same heaps, it's come from two words in equivalence class. So there is a bijection between commutation class of element and heaps of this element. So this is in general, this is a particular case of dimers. And see, this is a heaps of hexagon, the pyramid of hard hexagon. So you can do in heaps of cycle. So this is this is heaps of cycle. The complementary, so you can define, there is two possible definitions for heaps by level. See, this is level, when pieces fall one by one, this is level 1, level 2, level 3, level 4. Or there is a definition with a poset. There is various definitions. And people working in fully commutative element in Coxeter group, they prefer to work as a poset. So you have the graph. This is a graph, a non-commutation graph. So the letters of the alphabet are exactly this kind of point. Here they do not commute if you put an edges between the two, which means for dimers they intersect. And you can see heaps of such elements as you put some bar here. You have big ball like this, and if there is 2 points connected by an edge, then the big balls are big enough so that if they fall, they are going to touch each other when the projection is 2 points of the non-commutative graph. Or you can define this also as a heaps. There is a heaps above this. This is a maximal chain, and this is a maximal chain. So there is a definition with a poset. And for this symmetric group, you see the symmetric group is defined by this relation. So the heaps of dimers is going to be in bijection with such class, commutation class. And now the braid relation is equivalent to do this transformation on a heap if the two dimers are very close together. And the Coxeter group is exactly, Coxeter graph is very simple. So I will only show you the example for this very simple graph and definition in the Coxeter group. And a class is fully commutative if and only if all the reduced decomposition of the word, so using the commutation plus the braid relation, all the reduced decomposition make a unique commutation class. In general, the reduced decomposition are a union of different commutation class, and fully commutative means that there is only one permutation class. And the corresponding heap will be called fully commutative heap. So it's well known that the fully commutative element in the symmetric group is in bijection with 3-to-1 avoiding permutation, or there is only one commutation class. This is a Catalan number. But I am going to reprove this by using. So there have been many papers using heaps. Many papers, many classifications, stem rays, finite Coxeter group. Okay, so I will just show you the duality in the context of fully commutative group. So first, new notion, the stair decomposition of a heap of dimers. A stair in a heap of dimers is just this. It's a consecutive dimer. They're touching each other, and it's a maximal possible chain. So here is a heap of dimers. Here is a stair decomposition. And now I am going to give a bijection between heaps of dimers and heaps of segments. So I substitute this as a segment. So each of these segments, you substitute a heap of dimers, and you get a bijection. You get a bijection between heaps of diamonds with a stair decomposition and heaps of segments. So again, you have this duality between heaps of dimers, heaps of segments, and what is the relation with fully commutative class? Just a funny remark, that in the first part of the talk about Christian papers, and this segment was replaced by this. In this bijection with a stair decomposition, I have a stair, I have this segment. If you just do this, and then you get exactly the bijection of the beginning. But be careful, there is a trick in this stair decomposition. It's because it's generally function. There is a double. There is something you have to think about it. So the total order on the heaps of. So now I go back to the taking the leftmost or rightmost pieces. There is a so-called normal form of a commutation class. And so there is a Cartier-Fourier normal form, lithographic normal form. Each time you take the leftmost or rightmost pieces. So here I take the leftmost minimal piece. So 1, 2, 3, 4, 5, 6, 7, 8. And this is called the lexicographic normal form. So in a commutation class, you take a representant. Taking always the leftmost piece gives you what is called the lexicographic form, because it's the minimum for the lexicographic order if you have an order in the class. Sometimes it is called the Knut normal form. Knut doesn't like this at all. It's a lexicographic normal form. It is here. And so you can make an order on the segment. And this ordering the segment gives you a total order on the stair. And with this total order, then you can characterize a fully commutative element. Sorry to go very fast, but fully commutative element, if you don't have this, then, okay, here is to say it's fully commutative element means this is a stair decomposition. And this means that all this number E1, E2, E3, this last element go increasing, the index go increasing. Here the index go increasing. And so you get a fully commutative element in a symmetry group in bijection with this pair of two sequences, which are the Catalan number because they are in bijection with the Dick path. And this is the duality in the context of the first. And I have 1 minute to finish the third part of the talk. I mentioned the paper of Tyler Helmut about the Ising model on Sager, Castellin, so everybody knows it. And the solution, there was a solution by Kakwar, Chairman, with the determinant. And Helmut, he put some edges on this. So we have some circuit, and there is a condition on the path, and you need a second bijection. The second bijection is you follow your path, but instead of making a cycle and fall down each time, no, you are following with oriented edges, and you will fall down. It's an oriented loop of edges, and this is a second bijection you need in this, and it's cancelled. And then you use a third fundamental lemma in heaps of pieces, the logarithm lemma. And you can also use this non-backtracking path, which cannot be characterized by the first bijection. It's characterized by the second bijection. And there is many non-backtracking paths. So in this second bijection, I will finish. That's a second bijection. If you apply this second bijection to Dick path, then you get segment. You get the bijection between with Lukashevich. You get the bijection with heaps of segment and Dick path. So again, you have this duality segment and this follow the festival of bijection. And okay, that's it. So this is a bijection Dick path semi-pyramid with this is bijection using the third. This is Lukashevich. This is paper with Mireille Bousquet. This is all this commute, and you have a festival of beautiful things. And this is the top of the iceberg, as Christian was saying. Okay. Thank you very much.
So thank you, Xavier, for this beautiful talk. There are any questions? Maybe a question from the chat. Can you explain the Henkel determinants directly from it? The Henkel determinants. Les déterminants de Henkel, je ne sais pas comment on dit en français. Yes, the...
Oh, but I would take my... No, but the Henkel determinant is well known on orthogonal polynomial theory. I think there is a monograph by Xavier in '83 about this is a lemma. This is a famous lemma, the LGV lemma, le lemme à grande vitesse. That give you non-crossing paths in certain conditions are given by non-crossing configure by determinant going by non-crossing condition. And here the crossing condition is satisfied because it's dict path. If you were taking Motzkin path, Henkel determinant, it would not be satisfied. There will be plus and minus. But this is very classical. The LGV lemma is called by Christian.
So I see there are some other exchanges on the chat, but my computer switch off. So maybe you can read the chat, or maybe.
The book by Argo Bast, did he have the ballot numbers?
Ballot numbers. Ballot.
Well, ballot number was very...
The book you mentioned from 1800. Did he have the combinatorial interpretation?
Sorry. Can you repeat the question, because we didn't hear very well?
The book from 1800 by Argo Bast, did it have the combinatorial interpretation of the Catalan numbers?
No,
I think you have to repeat the question. Sorry. Try again.
In the book by Argo Bast from 1800, did he have the combinatorial interpretation?
No. No.
Yes.
No, he did not have any combinatorial interpretation. No, it was a general technique to compute some tableau of numbers you can add, defined by recurrence. And so he referred to Laplace probability book, and he don't speak at all with path, with ballot number, not at all, but this number appears in the context of, and he have many examples of this technique by tableau of numbers which are constructed by adding 2 by 2 the number. He have a beautiful technique, and this was one of the 10 examples. And in fact, he gave the formula for the ballot number. But he did not know any path. It was related to Laplace probability, the book of Laplace.
Okay,
thank you.
Philippe Di Francesco is asking if usual statistics on path lift to heaps, like, for example, area under the path. Do usual statistics on path lift to heaps? You can read it there. Just like... For example.
No, yes, it's possible. If you put some weight on the path, then you can get, for example, the bijection we get a long time ago with Mireille Bousquet-Melou about staircase polygon and heaps of segment. The staircase polygon, you get the area of the staircase, so you have a Q analog, and then you can transport the Q analog on the segment, and then you can relay the heaps. It works with Q analog, everything, and then you get the QBSL, because the heaps of segment is a pyramid, ratio again, inversion lemma, ratio of trivial heaps of segment. Trivial heaps of segment is the QBSL. And then QBSL appears, and there is a paper by Kim and Stanton recently in Archive, again in May, that it shows orthogonal polynomial, the Lommel polynomial, QBSL. So all this is coming, yes. Yeah. This is the power of heaps. You can put weight. As soon as the weight of pieces is independent of the height. So if you put some weight on the cycle, everything, then you get all linear algebra. There was some old paper by Zalberger, Fatah, etc., about proving combinatorially Kelly Hamilton, proving McMahon-Master theorem by usual technique. But if you lift this at the three fundamental lemma with the weight, you get everything. So this is, you know, I am looking this. I am not satisfied with bijection, etc. I try to combine all this bijection to have a unique principle, and I think this is this three lemma is. So you can you can get many things, and you know, because you are working on Laurentian I am going to show Laurentian triangulation relation. It's in Bayesian with heaps of diamonds, you remember, and there is a curvature in the quantum gravity, and if you want to really modelize, have the parameter curvature, you need to take this stair decomposition of the heaps of your heaps of diamonds in your paper. So the stair decomposition and this bijection diamond segment is again useful for quantum gravity. There was a talk about quantum gravity's meeting, and so.
Okay,
so
thank you.
You can do many things. So there is a video book. You just. See, I just mentioned this video book. It's all the heaps of pieces are in this video book. I was late in the train, so I cannot participate to the conference with a different book. But video book is it's a mixture. There is all the slides, a set of video, and in each video there is a full page, and you can you click on what you want, and then it goes directly in the video up to 1 second. So it's there is a discussion: what is best, a book or a video book? Or so I should stop because.
No, okay. So is there other? Oh no, okay. No other questions on the chat, and in the okay, Philippe.
Yes. So at the beginning you mentioned your duality between n and minus n, and so could you use that to give a combinatorial proof of the Riemann zeta function equation that relates values of Riemann zeta function as positive and negative?
No, but I have to think about that.
That's analytic continuation what you are doing. And it's,
but I have been working on the zeta function for graph.
Yes.
Because it's for a Riemann graph, the Riemann hypothesis is true, and zeta function for graph, then it's with the heaps. Many things can be explained with the heaps of pieces. There is hundreds of papers on zeta function for graph. There is a book in number theory. So I was very inspired with zeta function on graph. There is some paper by Giscard about showing the relation between zeta function in number theory and zeta function on graph. So I have to think about your question coming from the background of zeta function on graph.
The proof is putting together Catalan and Rouchet. If you put together Catalan and Rouchet, you get both sides of the Riemann zeta function equation.
Ah, so it should be. So it should be maybe.
So, but it's not. As you say, it's not combinatorics because on one side you have linear algebra, on the other side you have combinatorics. So
but this makes an interesting thing. When one side is combinatorics, the other side is not at all combinatorics.
Yes,
this is a fight between Rouchet and
exactly.
and Catalan and Delannoy.
Only combinatorics to prove that equation.
No, it's.
Okay, so but you don't know.
I have to think about it for the next.
Okay, other question?
Yeah, hi, so I'm Jonas Turunen, and I would like to go back to the quantum gravity a bit. So you refer to Lorentz and quantum gravity in the beginning. So do you mean the usual, like, bijection between, like, causal maps and hard multimer configurations? And then you have a heap representation of this, well, say, hard dimer configuration. So do you mean, is there something written in terms of heaps, or is it just like hidden in the?
Oh, and I think I was because with Philippe Di Francesco, there was they make a paper about Lorentzian quantum gravity in 2 dimensions with triangulation.
Yes.
It was worked by Loll and Ambjörn, and so they use heaps of dimers and then it's triangulation, and so I try to simplify to do, because it's a special case of Lorentzian triangulation on a cylinder. So if you cut, you have on a plane, and then there is a condition on the heaps of dimers. But if you take general heaps of dimers, a general Laurentian triangulation, then you get, you can connected heaps of dimers, and Mireille, with chemical Rechinster, they are given a generating function for this, which is not definite. So it's suppose Catalan for the regular triangulation is, but it's not definite. And then I gave a proof, a bijective proof in that case, for the what I call the Nordic decomposition of heaps of dimers. So that was the only original things I have done on this subject, and also to study the curvature, where you have to put segment and but I did not succeed to go further. And maybe Philippe can say more about your question.
Do you think that this could be generalized if you replace, say, dimers by some a large multimers? For example, that you have a large faces in your Lorentzian maps. I mean, causal maps. And then you would like replace Dick path by Lukasiewicz paths, basically, which have large jumps.
I don't know, but it should be. No, there is some work to do. No, it should be done. It's a beautiful combinatorics.
Yeah. Okay. Yeah. Thanks a lot.
Yes. Thank you.
Okay. Other questions? There's another question on the chat, I think. This one. I cannot.
Michel.
So yeah.
What I mean, do you have a bijection from non-intercept
in this context to Heaps directly?
No, it's an interesting question, Michel. Because not accepting paths, and if no, it's complicated. I should think about that. Or you should think about that. You follow the class in India about heaps of pieces and orthogonal polynomial. So please solve this, and when you have solved, then we make a joint paper. And it's interesting. There is another question that I'm going taking the. I see that you are going. We are taking alternating sequence. So it's because non-intersecting paths and translated in non-intersecting heaps. I did not think about that, but I should think. You too, because you are working with Untitled Determinant in London and a lot of things. And good question. Good luck.
Okay, so other question? No other question, I think. So let's thank Xavier again.